Hello, in this talk I will be presenting our paper titled Seamless Variability Management with the Virtual Platform, a work in collaboration with Daniel Struber, Thorsten Berger, Ralph Lamel and Mukelabai. Let's begin with an introduction. Due to varying customer requirements, software systems exist in many variants. A few examples of domains dealing with variant-rich systems are automotive and avionics control systems, robotics, and highly configurable systems such as the Linux kernel. For creating variant-rich systems, companies use two approaches. First, we have clone and own, in which developers clone a variant and modify it to create another one. Consider this scenario where a basic calculator is cloned and modified to create scientific calculator, which is cloned to create the financial calculator, which is cloned to create the graphing calculator. Clone and own provides developers more independence and fosters quick innovation, but maintaining these variants can be tricky. Consider that developers identify a bug somewhere in one variant. Due to cloning, this bug also exists in other variants. To fix it, developers have to manually perform clone detection to find the places the bug was cloned. Also, if the buggy feature was scattered across software assets, developers have to perform manual feature location. So clone unknown does not scale well with increasing variants. The second approach is a software product line where an integrated platform consists of all features implemented only once. There is a configurator that takes a feature selection and generates a corresponding variant with only the selected features. This approach makes changes such as bug fix propagation easy and allows experimenting with different configurations. However, it can be expensive and dependent on incorporating variability specific concepts such as configuration. The state-of-the-art solution is migration, which in itself is risky and error-prone. Our solution is to exploit the spectrum between the two by bridging the gap using different governance levels. The idea is to provide incremental benefits for incremental effort. Let's look into the governance levels using the same calculator example. We start with clone and own, but then we have clone and own with provenance. Developers still clone variants, but now we add traceability between clones and their source variants so that developers don't have to perform manual clone detection. Then we have clone and own with features. We advocate that during development, developers add the information about which features does an asset implement. We use the term feature mappings and they can be added in different ways. The benefit is that developers don't have to perform manual feature location. Next, we have clone and own with configuration, where we introduce variability mechanisms to also allow for optional features and variation points. Next, we structure the features we have into a feature model, which is a tree of features. This gives a high-level overview and enables checking validity of feature selections. The last level is an integrated platform where we reduce all code redundancy to provide better consistency and quality in variants. We propose a framework called the Virtual Platform to support using various product line concepts over the spectrum. Our framework supports clone management and incremental migration. We provide operators that offer dedicated support to move along the spectrum. The operators work on our conceptual structures, which are semi-structural representations of source code. We store and exploit two important kinds of metadata that usually get lost and make maintenance difficult, including features, feature mappings, and clone traces. Our framework is language independent. We provide a formalization and implementation of our framework and conduct a cost and benefit analysis of simulation of a real-world variant-rich system. To give an overview, the variant or the working copy is synchronized with our conceptual structure called the asset tree. The developers can then use the traditional asset-oriented operators or feature-oriented operators, both of which will be explained shortly, to modify the asset tree. Alternatively, they can integrate the operators into a development tool of their choice as commands and invoke them. They can also incorporate the operators into a version control system and synchronize the commands with virtual platform operators. Let's delve into the conceptual structures. We have assets which are any artifacts belonging to a variant, for example, a repository or a folder or even a class or a method. Assets are hierarchical, making every asset an asset tree, and they are also versioned. Then we have features. As previously mentioned, we advocate proactively recording feature-related information in software assets. Features are high-level functionalities developers are working on, and if their location is not stored, it makes maintenance very difficult. Having features facilitates migration to a product line, and there are a number of ways you can incorporate features into software assets. In virtual platform, features are mapped to assets using presence conditions, which are expressions of features that an asset maps to. The last conceptual structure is feature model, which is a tree of features. Feature models help structure the project into modules and capture the relationships and constraints among features. In virtual platform, assets of all types can have a feature model. Let's look into the operators. We have the traditional asset-oriented operators which synchronize the asset tree with the working copy. Those are add asset, remove asset, change asset, and move asset. Importantly, these operators are automatically and silently invoked in the background in virtual platform. Next, we have the feature-oriented operators, which are the operators used to handle feature models. They include add feature to feature model, remove feature, change feature, move feature, and make feature optional. In practice, feature model-related evolutions are far less frequent than asset-related evolutions. The operator for adding a feature model to an asset is add feature model to asset, and the operator for mapping an asset to a feature is map asset to feature. So let's look into how we store clone traceability. The idea is that during cloning, we store a trace between the original asset and its clone so that developers don't have to perform manual clone detection. Virtual Platform has a trace database, and every time an asset is cloned, it stores a trace pointing to the source asset, its clone, and version of the source at the time of its cloning. The benefit is that change propagation can be accurately and automatically done. So what are the benefits of using virtual platform? We can use it to query the system using a set of convenience operators we provide, for example, to get mapped assets of a feature, or get clones of an asset, or detect changes in an asset after cloning it. In addition, we can clone assets as well as the features they map to across variants using clone asset. Also, exploiting feature-to-asset mappings, we can clone entire features along with the assets that implement them into other variants. Lastly, we can track changes in assets and features and propagate them to their clones automatically without having to find their clones manually. We implemented our proof of concept tool in Scala and tested various scenarios covering the spectrum using FunSuite. For evaluation, we used a real-world case study of 4 variants and conducted a cost and benefit analysis of using our framework. We simulated the development of a special branch of the project, which also had feature-to-asset mappings. For every 2 consecutive commits, we got the git diff and retrofitted it to our operators. In the end, we counted the number of invocations of every operator. We have the incurred cost, which is the cost of adding features and feature mappings, and the cost of fixing mappings developers forgot to add. Then, saved costs are the costs of clone detection and feature location that we avoided. The benefit is the difference between the two. We assume that feature location takes 15 minutes. Also, clone detection takes the same amount of time. Lastly, adding a forgotten mapping costs 10 times more than adding it proactively. Based on these assumptions, if developers take 54 seconds to add a feature mapping, they reach a break-even point. In practice, adding features that are fresh in developers' mind while development takes significantly lesser amount of time, we envision greater accuracy if virtual platform is used alongside development. So to sum up, we propose an incremental migration framework that exploits the spectrum between clone and own and a software product line using 6 governance levels. Our framework can be integrated into development tools or version control systems or can be used directly. We provide a set of operators that offer dedicated support to move along the spectrum, and our evaluation on a real-world case study shows promising results. With this, thank you all for listening, and now I welcome your questions.
All right, so welcome back. I am joined here with 2 authors of this paper, Wardle Mahmood and Mukalabai. And we might be joined by a third author. We don't know. So do please add your questions to the chat. And if you can, remember to use the question mark button so that we can see that it'll actually highlight on our view that it's a question has been asked. So we do have a first question asking how intrusive, as in impacting the daily task of the practitioner, are levels to reach variant-rich systems, right? So what is the user experience in using this?
Yeah, that's actually a very good question. So how we like to think about it is that it can be perceived as adding comments, like you add feature related data into your code, but you won't have to think about the comments. So when developers are working on source code like they normally do, in their subconscious there is already something they know that they're working on. So this is, let's say I'm developing a mobile phone and I'm writing some code. So this would be for messaging, or this would be for mobile data. So what we say is that just take out some time and write it out in a very minimalistic way. So I would say that it's not too intrusive, and also we provide the flexibility of adding it at any point of time you want. So it's not essential that you add it alongside development, but when you are maintaining code, or when you think that, yeah, I remember that code, maybe that was for that feature, so let's go and retroactively add it later. Yeah.
I was going to ask, right? Because sometimes the feature that you're adding is cohesive, like a method. Sometimes it's scattered, right? And so do you have to, if you're adding something that's scattered, are you constantly, annotating every segment there that?
Yeah.
With the comments.
Yeah, that's also a good question. So it's not us that are annotating; it's the developers that are annotating. So
Right.
basically, how we sell it is that it is incremental benefits for incremental investment. Even if it is a scattered feature, and let's say it has 5 or 6 locations, you add in 1 or 2, you still have some benefit. But of course, there comes a time when when it's too detailed or too scattered, and when you are writing features as much as you're writing code. So maybe it's 5 or 6 lines of code, but one feature. Then I guess you might lose track of things or something. But there is still the chance of receiving the benefits of the annotations that you did add. So yeah, I can see that being a problem, but in our research group, we are already working on feature prediction. So when we have some source code that is annotated, then we can provide suggestions, or predict that this code looks similar to that code, and that code was mapped to so and so feature. So does this code also belong to that feature? So making this annotation system a bit more intelligent, so that developers can be facilitated in adding those annotations. Yeah.
Awesome. So new question. Do you see a role for traditional tools like Kconfig with all of your annotations?
So for now, we have annotations in our evaluation that had the Clapper syntax, but if we want to integrate it with Kconfig, it should be fairly simple, because we essentially need to add a few regular expressions, and then afterwards it's the same. You have some lines of code, and you have some features that are mapped to that. You have a feature model. So it's directly applicable. In fact, one of the future directions is to try to have a scalability study with the Linux kernel, so that we see that how scalable our approach is for very, very huge projects.
Yeah. So that leads into the next question. So I know that I'm familiar with the case study, and it is actually a fairly substantial case study. But there is a question about scalability, right? So if you've got a feature that really does spread out to a large number of files, 100 files or more, do you see an issue there? And you kind of said it's, if you have partial annotations, you still benefit. Do you have a way of measuring that, the benefit that you get from from partial information?
Yeah, so you have to the first is the effort saved, like in the evaluation. First is the effort saved. So if you have the annotations, then you can directly copy paste, or you can clone the features, or you can propagate changes using those feature annotations. And they are saving time and effort for both feature location and clone detection. But if you are not, then according to previous research, it takes roughly 15 minutes for you to locate a single feature and clone it in the other repositories, or do change propagation manually. So this is a very rough estimate, but yeah, if you miss out features, then you will you will have to spend time in feature location and clone detection. Right now there isn't like an exact measure of or formula that we can say if you miss 6 features you have to spend this much extra amount of time. It all depends on the size of the code base and the number of features. So yeah, it would be hard to give an estimate.
Yeah, so there's a bit of a more complication than that, right? Because if you're missing annotations, then your propagation is going to be missing propagations, right? And so it's not quite the same thing as, oh, my code isn't thoroughly commented, right? What we're missing are traceability links that are needed to perform the propagation, and the propagation isn't going to be complete without them. So there is a cost to not being, and is there any, have you done any work on trying to measure that?
So for the traceability links, there are 2 things. You have the feature to asset mapping, but then you also have the clone traceability, and that is relevant for both asset clones and feature clones. So in that case, there is no chance of missing any, because it is silently automatically stored in the background. If you clone an asset or if you clone a feature, that is automatically stored in a small database or something. And then you can traverse it using convenience operators and everything. So change propagation, that part can be efficiently performed. About these feature to asset mappings, yes, it is a bit expensive, or it is hard, it might be hard for developers to add those, but at the same time we are not proposing an essentially new paradigm. It is only that we are telling them to do something that they already know, write something that they already know of. So right now it's that, but if we take it one step further, make it a bit more intelligent, then we are increasing the chances of having as many mapped assets to features as we can. Yeah. But to extend on my answer a little bit, the focus of this paper was mainly on the formalization and implementation of the operators and the brainstorming about the operators itself. And the evaluation was like, we didn't exactly evaluate it with a project, but with a project that was already implemented, and we replayed its history. So when we use it alongside development, then we would have more accurate estimates of costs and benefits, etc.
Awesome. So this is a framework that can expand different base frameworks. So there is a question of, is there an impact on the usage model depending on what you're building on top of, right? So if you're building from Git versus building from an IDE, is there an impact there? And you have 50 seconds to answer.
Impact on what? Just to clarify the question a bit more, impact of what?
Oh, the impact of what you are extending, right? So if you're building on top of an IDE versus building on top of Git.
Yeah, that's also a very good question. Quickly, so we already did that for Git. You have well-defined operators in Git, and every operator in there maps to operators in our virtual platform, like addition, modification, and deletion. And the same is the case with maybe IDEs. So in Java, you can have directory listeners that can listen and tell the changes to our virtual platform, and then we can integrate it. So it's I think the easiest part, integrating our platform into existing IDEs or version control systems. That